So in the previous module, we had defined a Poisson process with intensity lambda, and then we defined what are known as its interarrival times, and we showed that for a Poisson process with intensity lambda, with the definition that we started with, namely that starts from 0 and increments are independent and increments are Poisson random variables. Starting with that definition, we were able to show that the interarrival times are IID exponential lambda. So what we're going to show now in this module, in the beginning, is that conversely, if I start with a counting process for which the interarrival times are IID exponential lambda, that means I start with a sequence of IID exponential lambda random variables, think of them as interarrival times, that means define the arrival times as the partial sums of this sequence, and then define a counting process based on those arrival times. That counting process turns out to be a Poisson process with intensity lambda, which means that we would get an equivalent second definition of Poisson process with intensity lambda in terms of its interarrival times. Remember that starting from our original definition of Poisson process with rate lambda, which we agreed to abbreviate as pp lambda, we had proved something. We had proved that remember the sequence of interarrival times? So that sequence of interarrival times for a Poisson process with rate lambda was shown to be a sequence of IID random variables with common distribution exponential lambda. So this we proved starting from our definition. But what we want to do now is, we now want to go the other way around. That is, we now start with an IID exponential lambda sequence, xn. With this exponential lambda sequence, we define the Sn sequence. Of course, S0 is identically 0 as always, and Sn sequence is a partial sum sequence of the X sequence. Now observe, from the definition is clear, because the Xn's are strictly positive random variables, you have S1 strictly bigger than S0, which is 0, S2 strictly bigger than S1, etc., etc. And moreover, Sn goes to infinity as n goes to infinity with probability 1. There are various ways of seeing it. You can see it using Borel-Cantil lemma, or another way of seeing it is by simply observing that the Xn sequence follows the strong law of large numbers, which means that Sn over n goes to the common expected value of x1, which is a positive number, and since Sn over n goes to a positive number with probability 1, Sn has to go to infinity. So that hypothesis needed for a general counting process holds here, and therefore you can now consider the counting process nt defined this way as for any counting process. What we will show is that this counting process, as we have defined using Sns as the arrival times, which in turn are obtained as partial sums of the X sequence, we show that this nt process is a Poisson process lambda according to our earlier original definition of a Poisson process. Of course, if we show that, then this will lead to a second definition of Poisson process lambda. So what is it that we need to show? We need to show that the counting process nt that we have just defined satisfies 1, n0 is 0, 2, that increments are independent, 3, increment has a Poisson distribution as given here. So nt minus ns is a Poisson random variable with parameter lambda t minus s for any s less than t. First, since s1, which is x1, is strictly positive, the property A, which is n0 equal to 0, is immediate. No event at time 0. As for C, let's first observe that nt is Poisson with parameter lambda t for every t positive. Now, in C, we are required to prove something a little bit more, but once we prove this, as an upshot of our proof of B, which we will see later, we will get that nt minus ns has the same distribution as n at t minus s, from which, in view of the fact that we are going to prove that nt is Poisson lambda t, C would also follow. So proof of the fact that nt is Poisson lambda t. Well, recall that for any n, Sn, which is a sum of n IID exponential lambda random variables, has a familiar gamma distribution with parameters n and lambda. Okay. Firstly, by the definition of nt, the event that nt equal to 0 is the same as up to time t no event has occurred. So the first event S1, time of that is greater than t. So you get probability that nt equal to 0 is probability S1 greater than t. But remember, S1 is x1, which is an exponential random variable, and for an exponential random variable with parameter lambda, we all know that this tail probability that it's greater than t, is e to the minus lambda t. So probability nt equal to 0 is e to the minus lambda t. Now let's turn to any n greater than or equal to 1. Let's try to calculate what's the probability that nt is less than or equal to n. Now remember, nt less than or equal to n means there are at most n events up to time t, which means, or the same as saying that the time of n plus 1th event is strictly larger than t. But Sn plus 1 is a gamma random variable with parameters n plus 1 and lambda. So we know what the density of that is. So we write this probability Sn plus 1 bigger than t as an integral from t to infinity of that density. That's exactly what we've done here. Now we have this integral, so we do integration by parts. On integration by parts, this integral splits into a sum of one term which is e to the minus lambda t to the power n by n factorial, and the second term of integration by parts gives us this integral. But then you can quickly see that this integral is nothing but the probability that nt is less than or equal to n minus 1, in the same way as probability nt less than or equal to n was the first integral. So what we have therefore is probability nt less than or equal to n is e to the minus lambda t to the power n over n factorial plus the probability that nt is less than or equal to n plus 1. From this, of course, by subtracting the second term of the right hand side from the left hand side, you get that probability nt equal to n is nothing but e to the minus lambda t, then lambda t to the power n over n factorial for every n greater than or equal to 0. So therefore we have proved that nt has a Poisson lambda t distribution. Now we prove the following. Fix any t greater than or equal to 0. Define L tilde t for t greater than or equal to 0, another process, by this formula. So n tilde t is n t1 plus t minus nt1. So this is the number of arrivals during the interval open t1 to t1 plus t closed. What we are going to show is that this process n tilde t is independent of nt1, and the process n tilde t has the same distribution as the original process nt. So what we do is we show this by exhibiting a sequence xn tilde of IID exponential lambda random variables which are independent of nt1, such that n tilde t is the counting process with xn tilde as its interarrival times in exactly the same way that nt was defined with the sequence xn as interarrival times. To be precise, the xn tilde sequence should be defined in such a way that if we put s0 tilde to be identically 0 and sn tilde to be x1 tilde etc. up to xn tilde, some of these, then we should have n tilde t is the maximum of n greater than or equal to 0 such that sn tilde less than or equal to t. Now, since n tilde t by definition is nt1 plus t minus nt1, it should be clear, we will see a figure, that the waiting time for the first arrival of the n tilde process would be nothing but the waiting time starting from time t1 till the first arrival of the process nt after time t1. Okay, so that would be the first arrival, waiting time of the first arrival of the process nt tilde. And of course, for k greater than or equal to 2, the waiting time between the k minus 1th and the kth arrivals of the n tilde process would be the same as that between the k minus 1th and the kth arrivals of nt after time t1. So essentially, nt tilde is looking at the arrivals of the n process only after time t1. So now you can look at this figure A and sort of see or identify what your correct interarrival times for the n tilde sequence should be. So here is how a formal definition. Xn tildes are defined like this. X1 tilde is nt1 plus 1 minus t1 as figure A suggested, and xn tilde for any n greater than or equal to 2 is nothing but x nt1 plus n. So it is clear from the above discussion and figure A that the process n tilde t equal to nt1 plus t minus nt1 is the counting process with xn tilde as its interarrival times in exactly the same way that nt is a counting process with xn as its interarrival times. So what we now show is that the xn tilde sequence are again IID exponential lambda, just like the original xn sequence, and moreover they are independent of nt1. So to do this, fix integers m greater than or equal to 0, n greater than or equal to 1, and positive real numbers S1, S2, Sn, look at the probability of this joint event. That is, nt1 takes the value m and x1 tilde is greater than S1, x2 tilde greater than S2, xn tilde greater than Sn. So this event we are going to write completely in terms of the S sequence. Note that nt1 equal to m simply says that Sm must be less than or equal to t1, but Sm plus 1 must be greater than t1. That is, if and only if nt1 equal to m. Next, x1 tilde greater than S1, x1 tilde is S nt1 plus 1 minus t1. So that greater than S1 means S nt1 plus 1 is greater than t1 plus S1, or S nt1 plus 1 minus t1 is greater than S1. But if we assume that nt1 is m, then in the presence of that condition, x1 tilde is nothing but Sm plus 1 minus t1, so that is greater than S1. And of course, in the presence of the event that nt1 equal to m, x2 tilde is xm plus 2, xn tilde is xm plus n. So that's what the second line says. Now what we do is, I say that this equals, so the first of all, Sm less than or equal to t1, strictly less than Sm plus 1 will be there, and then Sm plus 1 minus t1 greater than S1 is same thing as saying that xm plus 1 is greater than t1 plus S1 minus Sm, and that implies that Sm plus 1 is greater than t1. So the first two events are equivalent to Sm less than or equal to t1 and xm plus 1 greater than t1 plus S1 minus capital Sm. Moreover, these two events are determined by the random variables Sm and xm plus 1. And remember, xm plus 2, etc., all the way up to xm plus n are all independent of these random variables. And moreover, among themselves, their IID exponential lambda. So, using this independence and identicality of distribution and the fact that they're exponential lambda, I get this this factorization. And now the first probability that Sm is less than or equal to t1 and xm plus 1 is greater than t1 plus S1 minus Sm. To calculate that probability, again I'll make use of the independence of xm plus 1 and Sm. So I write this joint probability by using conditional probability and then integrate with respect to density. So Sm less than or equal to t1, I have to integrate from 0 to t1 with density of Sm. We just use f sub Sm for that. We don't need explicitly the form for the density. And then condition on Sm being equal to S, what is the probability that xm plus 1 is greater than t1 plus S1 minus Sm, and that is simply the probability that xm plus 1 is greater than t1 plus S1 plus S. Xm plus 1 being an exponential random variable with parameter lambda, that is e to the power minus lambda t1 plus S1 minus S. And then the second if there's a bunch of factors from j equal to 2 to n, that is just writing the probability that xm plus j is greater than Sj. Okay, now what we do is, in this integral, look at the integrand, I factor it as, there is one factor called e to the power minus lambda S1, so that factor can be pulled outside and clubbed with the other product and retaining the remaining portion in the integral. So that's what gives me this. So there is a product of n factors. These factors are e to the minus lambda S1, e to the minus lambda S2, e to the minus lambda Sn, and then there is an integral which is integral 0 to t1 and then e to the minus lambda t1 minus s f Sm s ds integral from 0 to t1. But then by the same argument as used before, this integral is nothing but the probability of this event that Sm is less than t1 and xm plus 1 is greater than t1 minus Sm. But then this event is exactly equivalent to the event that Sm is less than or t1, which is less than Sm plus 1, which in turn is just the event that nt1 equal to m. So at the end of the day, we end up getting this final result. So what we have proved is that the joint probability that nt equal to m and x1 tilde greater than S1, x2 tilde greater than x2, xn tilde greater than Sn turns out to be a product of n plus 1 factors. The first factor is probability nt1 equal to m, and the next n factors simply a product of the probabilities that x1 tilde greater than S1, probability x2 tilde greater than S2, etc., etc. So what all of this shows is, well, as I pointed out that in the second and third inequalities above, we made use of the fact that xm plus 1, etc., xm plus n are IID exponential lambda and are independent of Sm. Now, what we have shown, this factorization shows two things. Number one, x1 tilde, etc., x1, xn tilde are all independent. They are also independent of nt1, and moreover, x1 tilde, etc., up to xn tilde are IID exponential lambda. Now, since this is true for every n greater than or equal to 1, we have therefore proved that the xn tilde sequence are IID exponential lambda, and moreover, they are also independent of nt1. What's the upshot? The upshot is, if nt is any counting process with its interrival times IID exponential lambda, as we started with, then for any t1 greater than or equal to 0, if you define a new process, namely nt1 plus t minus nt1 as t varies, then first of all, this process is independent of the random variable nt1 and has the same distribution as the process nt. And the reason for that is, what we have shown is that the process nt1 plus t minus nt1, this process is a counting process based on the same IID exponential lambda interrival times, just like nt was, and that this counting process is independent of the random variable nt1. So now let's complete the proof that nt is actually a Poisson process with rate lambda. Now we already noted n0 equal to 0, which means property A in the definition of pp lambda. We have also proved for any t positive, nt has a distribution Poisson lambda t. But now for any s less than t, nt minus ns can be written as ns plus t minus s minus ns. Now, using the above result with t1 equal to s, in other words, look at the n tilde process with t1 equal to s, then nt minus ns is nothing but n tilde at t minus s. But n tilde process has the same distribution of the n process. So therefore, nt minus ns has the same distribution as, first of all, nt minus ns is equal to n tilde of t minus s, but n tilde of t minus s has the same distribution as nt minus s, and that gives you that nt minus ns is a Poisson random variable with parameter lambda t minus s, because we have already shown that for any t, nt has Poisson lambda t distribution. So this proves property C. Now we need proceed to prove property B in the definition of pp lambda. So what is it that we have to prove? Fix n many time points, t1 less than t2, etc. less than tn. Fix n non-negative integers m1, m2, mn. Then star is what we have to prove. That is, these increments are independent. nt1, nt2 minus nt1, ntn minus ntn minus 1. As a first step, note that if I define n tilde t as we defined earlier as nt1 plus t minus nt1, then you can easily see that nt2 minus nt1 is nothing but n tilde 2 minus t1. nt3 minus nt2 is nothing but the increment of the n tilde process, n tilde t3 minus t1 minus n tilde t2 minus t1, etc., etc. Now use the result that the process n tilde t is firstly independent of random variable nt1, as we have already proved. One obtains that the left hand side of star equals this. That is, the factor nt1 equal to m, probability of that comes out as a factor, separate factor. But now what we are going to do is, in the second factor, we are going to apply the same argument. The process nt tilde has the same distribution as the process nt, because it is defined again by an IID exponential lambda interrival times. So the same independence property as we applied just now for nt also holds for n tilde t. To be more precise, the process n tilde t t2 minus t1 plus t plus n tilde of t2 minus t1 will be independent of the random variable n tilde of t2 minus t1. So using exactly this thing exactly as before, if you look at the second factor, in the second factor again the first event comes out, because the first event would be independent of the remaining events. So that second factor would be factoring out as this. So combining this last result with double star, we see what we have proved is that the initial joint probability that we started with can be now written as a product of three factors. The first factor representing nt1 equal to m1 probability, the second factor representing the probability of nt2 minus nt1 equal to m2, and then the remaining joint probability. But now one can repeat the same argument over and over again to complete the proof of star. So this means that we are now ready to give a second definition of a Poisson process with rate lambda. So it's the second definition. A Poisson process with intensity or rate lambda is nothing but a counting process for which the sequence of interrival times is an IID sequence of exponential lambda random variables. More precisely, let xn be a sequence of IID exponential lambda random variables, and define S0 to be 0 and Sn to be the partial sum sequence arising out of the x sequence. Then if you define a counting process Nt based on the Sns, namely this, then this is called a Poisson process with intensity or rate lambda. The reason we are saying this is called a Poisson process because you can think of this as a definition, and what we have proved is that this definition is equivalent to the earlier definition of pp lambda that we had given earlier. Now we move to finding some other properties of Poisson process which would be very useful. So what we do is, for a Poisson process Nt with rate lambda, we are going to condition on the total number of arrivals up to and including time t positive, and then find the conditional distributions of other random variables of interest. Okay, so the general thing would be that we condition on the number of events, number of arrivals up to and including time t, and then conditioned on that try to find the distribution of other random variables of interest. So we start with the conditional distribution of ns given nt equal to n, where s lies strictly between 0 and t. In other words, given that exactly n arrivals have taken place up to and including time t, we want to find the distribution of number of arrivals up to time s for some s less than t. Well, when n is 0, that is trivial, because if you tell me that nt is 0, then clearly implies ns must be 0. So the conditional distribution is degenerate at 0. So now let's go to n greater than or equal to 1. Given nt equal to n, the possible values of ns are clearly 0, 1 through n. That is, if somebody tells you that there are exactly n arrivals up to time t, then it's possible that none of them happened before time s, or 1 or 2 or all n of them happened before time s. Now for 0 less than or equal to k less than or equal to n, I'm going to use properties of Poisson process with rate lambda to get that the joint probability that ns equal to k and nt equal to n can be written as the probability that ns equal to k and nt minus ns is n minus k. And then, because of the independence of increments, this is a product of these two probabilities, and now we know that ns is a Poisson random variable with parameter lambda s, and nt minus ns is a Poisson random variable with parameter lambda into t minus s. So we can write down these probabilities, do some algebra, and we end up getting this. So this is a joint probability of ns equal to k and nt equal to n. Now to find the conditional probability given nt equal to n, the conditional probability of ns equal to k, we have to divide this joint probability by probability nt equal to n, which is again as a Poisson probability. So you divide this expression by that Poisson probability and then simplify, and what we end up getting is this expression: probability that ns equal to k given nt equal to n is n choose k s by t to the power k 1 minus s by t to the n minus k. Of course, this is a very familiar distribution. So what it says is, given nt equal to n, for any s less than t, the conditional distribution of ns is binomial with parameters n and s over t. Let's now go one step further. Suppose now we fix two time points s1, s2 less than t. So let's also say s1 is less than s2. We want to find the conditional joint distribution of ns1, ns2 given nt equal to n. That is, given that exactly n events have taken place up to and including time t, we want to know, conditioned on that, how many events took place before time s1 and how many events took place before time s2. So of course, because ns1 is always less than or equal to ns2, which is less than or equal to nt, for s1 as less than s2 less than st, we need only find this probability that ns1 equal to k1, ns2 equal to k2 given nt equal to n. We need to find it only for integers, non-negative, k1 less than or equal to k2 less than or equal to n. Because for any other k1, k2, the conditional probability would be 0. So first we find the probability of all three events. So we find the probability of all three events, intersection of all three events. ns1 equal to k1, ns2 equal to k2, and nt equal to n, probability of all three happening together, then we'll divide by the probability nt equal to n. And of course, the strategy is exactly as before. We write these three events in terms of the increments and then use the independence of increments and the fact that increments. So we write this event in terms of increments and then use the fact that the increments are independent and also the increments have a Poisson distribution. So we write that and simplify, and this is what we get. Now if we divide by the probability that nt equal to n and do some simplification algebra, this is what we will get, that for any two numbers s1 less than s2, both less than t, and integers non-negative k1, k2 with k1 less than or equal to k2, k2 less than or equal to n, the conditional probability that n s1 is k1 and n s2 is k2 given nt equal to n turns out to be this quantity. That's just simple algebra. So what does this result say? This result says that let s1, s2 be satisfy this, that is s1 is less than s2 and less than t, and suppose n is greater than or equal to 1. Then conditional on nt equal to n, the distribution of n s1 comma n s2 is like the distribution of xi1 comma xi1 plus xi2, where xi1, xi2, xi3 is a multinomial with parameters n s1 by t, s2 minus s1 by t, and t minus s2 by t. So look at a three-dimensional multinomial distribution with these parameters. Then look at the random variables xi1 comma xi1 plus xi2. The joint distribution of xi1 comma xi1 plus xi2 is exactly the joint distribution of ns1 comma ns2 conditional on nt equal to n. Now this can be generalized very easily. We leave it as an exercise. Instead of 2 time points, you can take m time points, s1 less than etc. less than sm less than t, and take n greater than or equal to 1. Denote xi1, xi2, xim plus 1 to be m plus 1 dimensional multinomial random vector with these parameters. Then conditional on nt equal to n, the vector ns1 etc. up to nsm is conditionally jointly distributed as xi1 comma xi1 plus xi2 comma xi1 plus xi2 plus xim, where xi1, xi2, xim plus 1 are m plus 1 dimensional multinomial with those parameters. To be more precise, this is something you can actually deduce. The above findings seem to suggest the following. Let's try to get a heuristic understanding of this. What do all these things say? This conditional distribution. Of course, we derived them, proceeding mathematically, but let's get an intuitive understanding of what they say. So given that there are exactly n, let's say greater than or equal to 1, arrivals during a time interval 0 to t, the times of arrivals behave as if they are n independent random variables taking values in 0 to t, such that for each of them the probability of lying in a subinterval I within 0 to t is proportional to the length of I, that is, the probability equals 1 over t into length of I. Okay? Because you see, when you looked at the binomial thing, namely that given nt equal to n, what's the probability that ns equal to k? So we saw that the conditional distribution is binomial with probability parameters n and s over t. So it's as if there are n independent tosses or n independent trials. Each trial has success probability s over t, and you're asking what's the probability that there are k successes in n trials. But here success means that in arrival there are total of n arrivals corresponding to n trials, n independent trials, and successes are those arrivals which happen before time s. So success probability is s over t, and that sort of fits in with this. Of course, this is only a heuristic way of understanding this. We do not know whether this is correct or not. So that's the question that naturally comes. Conditional on nt equal to n, do the n arrival times s1, s2, sn behave exactly like n independent random variables with each having a uniform distribution on 0 to t? Because earlier findings really suggest that this could be one possibility. It turns out that this is almost correct, except for the fact that the n successive arrival times are ordered. They cannot be really independent, they are ordered. So what we will show is that given nt equal to n, the conditional joint distribution of s1, s2, sn is exactly the same as not n independent uniform 0t random variables because they cannot be independent. However, it's the same as the joint distribution of the ordered statistic based on n IID uniform 0t random variables. So roughly they are like you have n independent uniform 0t random variables, but then you ordered them. Whatever you get, that represents the n arrival times S1, S2, Sn. So to begin with, in this module, as we said, we first sort of illustrated that the definition of Poisson process that was given in the beginning as a counting process with independent increments starting from 0 and increments having a Poisson distribution. Starting from that definition, we were able to show that there is an equivalent definition whereby we start with an IID exponential lambda sequence of random variables, think of them as interarrival times, define the arrival time sequence by looking at their partial sums, then the corresponding counting process again becomes a Poisson process with intensity lambda, thereby giving a second equivalent definition of Poisson process with intensity lambda. But then after exhibiting that, the next thing we looked at, which was something that we did towards the end, is tried to find conditional distribution of various quantities conditioned on the number of events happening up to time t. In particular, given that there are n arrivals up to time t, we asked in the beginning, what is the conditional distribution of the number of arrivals up to some time s for s less than t? And then more generally, we also found the conditional joint distribution of number of arrivals up to time s1, up to time s2, etc., up to time sk, all of them less than t, conditioned on there being a total of n arrivals up to time nt. Now, in the next module, we are going to continue with this work, namely finding conditional distributions of other interesting quantities based on or conditioned on n arrivals up to time t.